We just had an ITC colloquium by Witt from Northwestern, and we'll hear more from her about she spoke about gravitational waves, but now she will speak also about the sources, supermassive black hole binaries from simulation to observation. Even though the ITC is all about theory, our best friends are actually observers. And then we hear from an observer, Martin Elvis, and from the CFA, he will tell us about accelerating Astro 2020. That was during the pandemic, right? Some of us were not here. With SpaceX Starship. That should be quite interesting. And so far, the Starship exploded. Yeah. Elon Musk just gave his speech a month ago in terms of the forecast. He thinks it will succeed. Then we hear from Samantha Scibelli. Is that correct?
Scibelli.
Scibelli. It sounds Italian.
It is.
From NRAO about probing the complex chemistry in the earliest stages of low mass star formation. And finally, we'll hear from our own Jenny Calahan, and she will tell us about how the planet-forming zone is impacted by the surrounding radiative environment. So we'll start with Katie.
Okay, yeah.
Dim the lights.
Thank you. Okay, so for the lucky few of you who were at the colloquium talk earlier, you all got my introduction to this talk. But for those of you who were not, don't worry, I will give a brief overview. But feel free to come ask me later. I will be here the next 2 days. So today, like you said, I will be talking about supermassive black hole binaries all the way from simulation up to eventually, finally observing these really complex systems that I think personally are really exciting. So this is mostly what I talked about during the colloquium earlier, but for those of you who weren't here, the very exciting news from my collaboration Nanograv this year, as well as the International Pulsar Timing Array community, is that we are at last starting to see evidence of a stochastic gravitational wave background at these very low frequencies that are so far only probed by pulsar timing arrays. So the really important context for this talk is that while we're starting to see this gravitational wave evidence, we are not yet certain of the source. And there are a few things it can be. My interest, as you may have guessed from the title, is supermassive black hole binaries. These are expected to exist throughout the universe, and while they're all emitting overlapping gravitational waves, they're summing up together into the stochastic red noise signal that we model as this background. However, what we certainly hope is that there are individual gravitational wave sources, these supermassive black hole binaries, that will stand out from the crowd, that we would be able to see peeking out above the gravitational wave background as a continuous gravitational wave source. This is where my expertise mainly lies. So in Nanograv's 12.5-year data set, we were able to constrain our limits to supermassive black hole binaries across the entire sky, as well as our entire nanohertz frequency band. In this paper that I led for the collaboration that was released in 2023, we can see our overall sensitivity to supermassive black hole binaries. This is at a frequency of about 8 nanohertz. And we can see that our sensitivity is not even. We have many more pulsars on one side of the sky than the other. Those are represented by the stars. And as might make sense, we are more sensitive to gravitational waves on one side of the sky from the other. And that means if we were to place an example supermassive black hole binary at a mass of about 10 to the 9, we would be able to see it if it were farther away on one side of the sky than the other, over here, where we have fewer pulsars. Our horizon limit is much lower. So despite this, we are working continuously and learning from the evidence of the gravitational wave background to say, okay, this might be up next. We are trying to get as sensitive as possible, push our upper limits even lower in future data sets to start preparing to actually look for these sources. And the other important thing is that you can see there are a few diamonds on this plot. These are galaxy clusters that may host such a binary, or a few binary candidates that could be interesting to target, to look for specifically in this pulsar timing array data. So the one model that I wanted to mention is specifically this Doppler boost model, where if we have these two black holes, nominally each of them has an accretion disk. If they were orbiting around each other, one might move toward us, the other one might move away. These things are moving relativistically, so if we were observing them over a long baseline, we would see the quasars themselves get slowly a little bit brighter, and then a little bit dimmer as the brighter black hole moved away. So this is one way we use to look for those galaxy candidates that I showed on the previous slide. However, there is some complication to doing this. Even in the best time domain survey, quasars are themselves randomly variable. And not only just in a Gaussian white noise, they actually use this red noise process called a damped random walk. That is our best fit model for quasar variability so far. But this does provide the complication that when we put this into Fourier space, it can very easily be mistaken for a periodic signal. And even just looking at this example of a damped random walk up here by eye, you can sort of see why. It slowly varies away from the mean and back to the mean in a way that, if you're looking for a very slow periodic signal, could look very similar. So the question here is, if we are looking for these periodic quasar candidates in a long time domain survey, how can we actually differentiate this noise process from the periodic variability that we are looking for to find evidence of a binary and to actually properly estimate its significance? No? There we go. Okay, so many surveys have done this, and there have been many promising candidates found. Here I'm showing a light curve of one of the most quoted candidates, PG1302, that you can very clearly see a periodic component, but the jury is still out on trying to reason whether, is this just, stochastic variability? Is it periodicity? We need to observe it for longer and more repetitions of that cycle to actually see if it deviates. But the thing I always like to mention is that there are some excellent surveys that are going to be coming online in the next year or two. My favorite is the Rubin Observatory is going to start the Legacy Survey of Space and Time, which will visit all of the southern sky and beyond over cadences that are fairly unprecedented, also at an unprecedented depth. So this survey, plus coupled with the ones that have come before it, hopefully will provide an excellent data set to look for binaries in. So what I wanted to do, and this is something that I continue to do to this day, is make sure that we have actually practiced not only searching for these periodicities, but disentangling them from this natural quasar variability to actually look for candidates in current surveys as well as LSST and other future surveys. The way we've done this is essentially just by practicing. We simulated many, both periodic and damped random walk only quasars to actually go and put through a Bayesian model selection and parameter estimation to see both how well can we recover that intrinsic periodicity, which ones can we recover and which ones do we miss, which ones confuse us, and also just how accurately and which ones do we recover at all, how sensitive are we. And the important thing that we learned is that in future surveys like LSST, we actually have a much lower false positive rate, mostly coming from the cadence of these future surveys. So we can see in this plot here, we're showing our true and false positive rate for a current survey, namely a Catalina real-time transient survey, as well as LSST. The true positive rate in red is more or less the same for all areas of the damped random walk parameter space, but the LSST false positive rate in blue is much, much lower. So we're hoping that this cadence will let us actually, on a short time scale, be able to disentangle this long, slow periodicity from the intrinsic variations. Okay. And the context for this, in my last few minutes, is the fact that these are a perfect multi-messenger opportunity. For as we are looking for gravitational waves with pulsar timing arrays, if we see one of these periodic quasars or identify a binary candidate with a different method, it's essentially just waving at us from one side of the sky map and saying, look over here. You don't need to waste all of your computational power searching over every iteration of parameter space, every frequency, every sky location, and we might be able to get a little bit deeper. In fact, we learned that we are indeed able to get deeper. This is a project that I led for Nanograv showing that for a classic supermassive black hole binary candidate 3C66b, we can set lower limits than all sky searches on this individual candidate, and we can come near to ruling it out or confirming it. And we're optimistic that in the next few data sets, we will be able to do so. Here, we've limited its mass to about 1.5 times 10 to the 9 solar masses, which means we're getting close to its nominal mass that is derived electromagnetically. The interesting thing that we can do computationally by using this multi-messenger method is we can actually start to test the binary models themselves and search across frequency space because we've reduced our parameter space by searching across the sky and some of the other orbital parameters. So if we gradually start to relax the frequency estimate that we've derived electromagnetically, we can see that our gravitational wave mass limit does not actually start to increase until we're searching a very significant part of the PTA frequency space. So until we're searching approximately the entire space, our mass limit goes up very significantly. But beforehand, we can search a few orders of magnitude in frequency space before we actually lose sensitivity. So this is something we can use, hopefully, as we get these multi-messenger limits to actually start to weigh in and help the electromagnetic surveys verify candidates. So we've been making very steady improvements in this multi-messenger search. We've learned that they allow significantly faster analyses without losing any accuracy. As you can see from this plot that was led by Maria Carisi, we can see that using multi-messenger techniques allow us to simplify the gravitational waveform without losing any accuracy, but running much faster, as estimated by the MCMC autocorrelation length. So I'll end here with this slide, but there's so many exciting things that are coming up next, like learning how to jointly model a background in gravitational waves and continuous waves, how the gravitational wave background can inform our expectations, and how we can make these more efficient. So exciting times are ahead. Thanks.
When you were discussing the relativistic filling or closer effect, but there is another way to verify a binary, and that is the broadline region of the shift, and that is a spectral signature. Can that help a lot in figuring out the real ones?
The frequency ranges are not quite the same. I think the spectral information comes at a slightly wider separation than the gravitational waves nominally can probe. But I think there is a small amount of overlap. There's also some other modeling, such as what Magda does, where we're looking for this periodic accretion, so that can make a different signature. And one of the things we really want to do in the future is be able to incorporate all these types of information, as well as jointly model it with the gravitational wave, so we can actually do a joint likelihood approach.
Yes, please.
To comment on your question, it's not possible for massive black holes because if you want to get spectral signatures, you have to be close. And the broadline region, it will be a common envelope physically.
Well,
so you can do it only in intermediate mass black holes, actually. They separate only 9 gauges. And then this technique will not work because the period will be 1,000 years.
Yeah.
Well, the broadline region is 10,000 gravitational Schwarzschild radii, and that's roughly a period of a year or a few years. It depends on the mass of the black hole, but we're talking about years, which is your period, isn't it?
Yeah,
So I
it's,
think, well, it depends on the mass of the black hole, but there would be a range where the broadline region will be shifted back and forth because of the binary dynamics.
I've typically seen it as the wider separations, but yeah, I think it really depends on the modeling, which is improving.
Okay. Josh?
There's another way to get a periodicity, which you didn't mention, precession of a jet.
Yeah, absolutely.
What is the period that you derived for 3C66b?
Yeah, so 3C66b is actually identified from yet another method where it's actually seen to be precessing like as its location on the sky of the jet's core. That one is very near to a 1-year period, which is why this thing is reputed to be very massive, which is why it's a great test candidate. But that 1-year period, we have no idea. And there are follow-up observations that are being used to look for it and see if they can actually phase connect that period or see if it's evolved, which would point to a black hole origin. And yeah, there have been a couple great candidates that come from this jet precession. I think those, again, tend to be a little bit more widely separated, but again, it depends on the modeling. And that one is hard to do, you know, a very firm model selection because supermassive black hole jets can precess on their own. So actually trying to figure out, is there a binary causing that wobble or is it just intrinsic precession, I think is a difficult question. And that's something hopefully that, you know, a gravitational wave source would be able to disentangle. But again, we would need to get lucky and detect it first.
Yes.
So from your plot, it appeared that the horizon that you're looking at for the detections in gravitational waves is about like 100 megaparsecs or so. So I was wondering, so given that this volume is relatively small, these supermassive black holes are probably reasonably bright. So which parameter of LSST, is it the cadence, is it the depth that is helping improve on, say, what you couldn't already do with CRTS and ZTF combined? Why do we need an 8-meter telescope to look at nearby sources?
Yeah, so, and I think that is a multifaceted question that I really like thinking about is, you know, like you said, LSST is going to be looking at these really deep sources. So while these might be farther away than we actually would look at for a continuous wave source, we're not going to be able to see them that far away unless they're very, very massive. They can tell us a lot about what the population of binaries is like, which then we could actually test against our measurements of a gravitational wave background, because it's the binary population of a whole that actually builds up to make that background. So it's kind of this multifaceted approach of combining the electromagnetic data, testing it against the gravitational wave data, then we can revise our population models and see what we expect for the bright, loud sources.
Yeah, please.
I have a technical question on, so in the AGN model, the Dampier-Nawang is the best model that we have, but we know that it's actually non-stationary, meaning that, those functional parameters to describe it actively change in time.
Yeah.
Which makes a lot of sense. There are blobs of gas falling for all of them. I think that should cause some concerns when trying to find periodicity. Can you comment on that?
Absolutely. And this is something that I'm really excited to work on revising in the next few years. This is really working with, you know, it's a 5-parameter model, which is great. It runs compared to PTA data, I think it runs fast. But it's something that I think we can learn a lot from both fields about how to actually do that disentangling and model that quasar signal a lot better. You know, I call it noise, for other people it's signal, and there's a lot to learn. But, you know, us in PTAs who are used to doing that modeling are very used to using multiple noise terms that we have to actually model out alongside our gravitational wave searches. I'm really hoping to bring some of that expertise over to this problem so we can make those you know, noise, damped random walk parameters more and more accurate to actually see what they will do and, you know, look alongside them, but also learn more about where the biases might lie. So I would actually love to talk to you about that.
So Caitlin, just to summarize, in the literature there are people claiming that black hole binaries, if you integrate over cosmic history, just don't make enough to explain the PTA signal.
Yeah.
Then there is another group saying, actually, there should be more than enough, and in fact, that you need some gas to bring the binary the tighter orbit faster than just rotate. What is your take? Do you think it's too much or too little?
I will say that I think it's loud. I think it's louder than anybody expected. Whether that is, concerning, do we need to revise the models, or exciting, yes, this is great, we can detect it, depends on the day and who you talk to. I think one of the other more interesting things is, I'm a binary astrophysicist. I certainly hope it is a binary background, but there are other physics models that could induce a gravitational wave background that we will learn more about as we are able to constrain the spectral index better and better. So, it also could be something else. So no matter what, it's going to teach us something. And it's a measurement, and hopefully we will be able to model what is causing it better and better as we go.
And you are young enough to find the answer to us. Let's thank Kate.
Thank you. Okay, thank you. Can you hear me? Yes. I'm going to talk about an article that came out a year ago in, oops, this isn't started? Yes, it is. Okay. In Physics Today by myself and Charles Lawrence of Caltech and JPL and Sarah Seeger of MIT about accelerating astrophysics with the SpaceX Starship. It's, I think, an opportunity that we're very lucky to have that can revise what the decadal survey said. And that is the QR code for it, but don't rush, I put it on every slide. Okay, the Astro 2020 decadal survey, what are we going to do in the next, for big missions in particular, for the next decade in principle, but actually 3 decades at least in practice. The main thing is they recognized it as a basis for their recommendations for big space missions at least, that you need spectrum spanning capability to do 21st century astrophysics. And I think since then, they didn't know this, but JWST is proving this. There's this wonderful observation of UHZ-1, a lensed object, and to back up the JW observation, there is a handful of Chandra photons, and that's what tells you it's a supermassive black hole. Whereas with the red dots that are being found in JW, you don't have that information, and everybody's completely lost about whether it's starburst or AGM. So it's a nice proof that they were correct in their assertion. So they recommended a set of 3 flagships to span the spectrum. There's a far infrared one, which is based on the Origins study. The Habitable Worlds Observatory, which is based on the HabEx and LUVOIR studies, and the X-ray Lynx, X-ray flagship based on the Lynx mission. And I won't go into the details, but notice the factors we're talking about compared with today's missions are orders of magnitude, not 1, not 2, but typically 3 or even more in some cases, like starlight suppression. They're huge and wonderful instruments that we should really build. The problem is, when you look at the timeline that was put in that, this is straight from the Decadal Survey report, the first flagship would be the Habitable Worlds, as it's now called, and that would go in 2045, which is 21 years in the future, and for those of you with long memories, that's almost the same as thinking back to the launch of Chandra, and most of you, I doubt, were aware of the launch of Chandra when it happened. That's a daunting schedule and is a real crisis, I actually think, for the field. It's quite possible we'll go 50 years between the launch of X-ray flagships, or far-infrared flagships for that matter, right? I think that's going to be terribly to the detriment of the field. And I hope we don't see that, and so what can we do about it? Well, that schedule is driven by the cost they were forced to assume they were given by NASA to do, and then by the estimated mission cost, which is at least 10 billion or more for Habitable Worlds and 3 to 5 billion each for the other 2 flagships. So that's a problem. Could the cost significantly be reduced? How much are we looking at? Fabio Pacucci, who is here, I think, And is it your birthday? I think it is. Facebook told me it was, so I gave you this present.
That's great, Martin.
Okay, just what you wanted. He did a little playing with these NASA-type stand charts and found that a 15% cut in the cost of each would allow us to have all three operating at once instead of in series, which of course is what we want. It doesn't really accelerate the schedule yet, but it's an example. But 15% is still of order $1 billion, so we've got to look for some serious savings. And if we can do a little bit better, we can really accelerate this schedule, pull it all forwards. So why do they cost this much? Because limitations of mass and size lead to great complexity, and complexity costs a lot. With the current launchers, the mass can often dominate. For instance, the total mass of JW is just over 6 tons, and that immediately required a new type of mirror technology compared with Hubble. There are other reasons too, but that absolutely required it. Similarly, the size had to fit within a 5-meter fairing, in this case of Ariane 5, and that meant folding the mirror. And you may have noticed at launch they were going on and on about the 344 potential single-point failures that came, and we were all very tense while it unfolded. It worked magnificently, and it worked magnificently because they put an enormous amount of design effort into every single one of those 344. Design effort, manufacturing, and testing. Testing and testing. So that costs a lot. If you could eliminate 344 single-point failure possibilities, you've saved a lot of money. I won't put a number on it, but it's going to be a lot. So can we find savings in the 3 parts of any mission? One is the launch, then the spacecraft, which provides communications and computing and power and so on, and the payload itself. So the answer, I think, is yes, and if so, it opens up the huge design space with these new launchers. Why? Because these new launchers have several times the mass capability to a high orbit and several times the volume and don't cost NASA astrophysics anymore. So SpaceX Starship, which had a RUD on its first 2 tests, but we hope that the 3rd one will be a success. We'll find out. Look at those sizes. We're looking at 8-meter diameters and 100 tons to LEO, maybe 150 tons to LEO, and with refueling a similar mass to essentially any orbit we choose. Space Launch System, very expensive, but free to NASA because they can't, to NASA Astrophysics, because we can't possibly include that in the budget. So the only way we would use it is if it's given to us. Similar specs, new Blue Origins, new Glenn. Slightly smaller capability, we don't know the cost, we don't know the time. But the good news is we're not relying on a single launcher here, but we're going to use Starship as the example. So what could you do by having a lot more mass? Well, one thing you could do is save money on the solar panels and yet have more power. Starlink already uses silicon solar panels instead of germanium multi-junctions, which cost 200 times more. You could have 10 kilowatts of power instead of 1 kilowatt that Chandra runs on. And that means you have a lot more choice in your electronics. You can use shielding, to shield the electronics and the cables. You could also have many copies of the electronics. So you have a voting system, which the Falcon 9 uses right now. Even the simple mechanical structure could be built with normal engineering tolerances of factors of 2 or 3, not the very tight tolerances that spacecraft currently have to go through, which leads to much simpler design and much simpler testing. We're not the only people to have made this point. We think we were first, but Dan Goldin just now had another article in Aerospace America where he pointed out that we can do this kind of work. And there's a startup who've raised a couple of tens of millions, K2 Space, pointing out that that's been a problem and they intend to get around it. And so good, it's a sort of movement, which is what we need. Astronomers alone probably won't be enough. So for example, the only entry into the studies that made use of larger launchers was the Origins study for the far infrared, but this points apply also to the optical UV and near infrared. you can drop a 6.5 meter mirror into the fairing of one of these new rockets, and you don't have to fold anything. And that means you don't have to, you've eliminated hundreds of single point failures. You don't have to have a tennis court size heat shield, because you can wrap the heat shield around the telescope. And this is only the beginning. This study did not look at using all the mass to save in other cases. There was a mirror material choice that could be simplified if you can have more mass, and of course all those spacecraft savings. A totally different case is the X-ray flagship. The Lynx study did have a rather large number of small segments to the mirror, and they were only 0.5 millimeter thick. And this was driven by the need to have a mass for the mirror that was a reasonable number, like 2 tons. If only you could have 4 times thicker segments, you would get 4 cubed, 64 times stiffer. And this comes from Alexei Vaklinin, who pointed this out. The rest is up to me. It's not your prediction. But my bet is that that would lead to far simpler fabrication, larger pieces to deal with, much easier alignment and testing, therefore. But it would be an 8-ton mirror, which is more than JWST's total mass. So what? This is still a small number compared with what these new launchers can put up there. So we shouldn't worry about it. We should just go ahead and look and investigate just what those savings would be. There's one more thing, mission creep. This is what the problem of scientists. Scientists will always say, like the poet Goethe, we want more light. He did it on his deathbed. We hope not to do that. They will always say, well, why, if you can get a 6.5 meter mirror, we could do so much more with an 8 meter mirror, but 10 would be really good. And immediately you give way to that kind of pressure, you're back to folded mirrors, you're back to hundreds of single point failures. We've got to avoid that. So no, we mustn't do that. We must do cheaper and faster, yes, but not better, because our goals are already very ambitious. There's no need to do better. We're talking orders of magnitude improvement. So what we've called for in this paper is that by the time of the mid-decade review, somewhere around 2026, all these 3 rockets will have been proven, or not, but we can be ready in case they do work by studying all of these flagships in this new paradigm and asking, the primary question we're asking is, can we save serious money? And I think we should talk billions, but that's really up for experts to decide what can be done. And we should also design in a cost containment system to rein in those scientists, because you know what they're like. They'll just ask for more. So thank you.
Elon wants to get to Mars. NASA wants to get to the moon. Do you see a future for astronomy on these platforms, or do you think?
Yes, and the talk I was tossing up with which talk I should give you, and the other one is protecting astronomy sites on the moon for a whole range of interesting possibilities. Now that people are going back to the moon, there are astronomers around the world who are thinking, in that case, I could do a far infrared telescope and a cold trap, a gravitational wave array in a permanently shadowed region, and things like that. And we had a meeting at the Royal Society, Joe Silk and I and others organized it, and it's looking very promising. And the IAU actually has formed a working group on astronomy from the moon, and I'm one of the co-chairs to try to protect these sites and to promote the idea.
So if you had a one-way ticket...
No, I would not, no. The restaurant scene is terrible there.
Hi there, this was a very fun talk, thank you.
I'm very serious.
I'm very serious. My question is, there's this whole other way of thinking about the future of astrophysics spacecraft that rely more on the future of high-precision station keeping.
Mm-hmm.
Truss structures are an artifact of our, thinking in terms of gravity. We're in a microgravity environment. Inflatable structures. When I reflect on your talk, I just wonder if we should be pushing more in this direction.
I would like to push both. My feeling is that right now we get this once in a lifetime, pretty literally, a once in a lifetime opportunity to take advantage of these specific new rockets with these specific proposed missions, and we can save billions and get them up and working. Right? In the meantime, as we get commercial space stations, which are very likely coming, in fact, surely coming, there are several contenders, there will be a lot more construction in space being done commercially, and they will bring the cost down to where we won't be experimenting with it, but for astrophysics, which is a very expensive idea, but we'll just use commercial capabilities, and we will build these big UV interferometers, for instance. That would be wonderful, but I think it's the next step.
Thanks for that, Martin. That was so interesting. Another way that we can consider reducing costs is taking all the lessons learned from the other mega projects that humanity already does on Earth. So there's a great book I recently read called How Big Things Get Done. If you haven't read it, and I've been looking to that as yet another mechanism to reduce capital observatory costs. Because really, an $11 billion project is not huge by humanity's scales. So there's lots we can learn.
It's big dig scale, for those of you who are here. And
it uses that as an example.
Yes.
Anyway, I recommend that one.
Yeah, compared to, I guess, the Apollo program.
Yeah.
It's very more questions? Comments? Yes?
Do you know if there are any thoughts about it in China?
We have not mentioned China because NASA is not allowed to talk to China. Congressional mandate.
I mean, are they thinking about something similar over there?
Well, they are building. There's now a commercial prototype. A commercial company built a prototype, which is basically a copy of the Falcon 9 and doing the landing. I don't think I've heard of them doing anything on this super heavy scale, but I wouldn't be surprised if they do very soon. And I don't think I've heard of anything on this scale, on the scale of these flagships, from anywhere else. They're building a Hubble scale 2-meter telescope. Yeah.
Isn't science supposed to be international? I don't understand why
Yes.
NASA cannot speak to the Chinese.
It's not up to NASA. I'm sure that we'd love to, but it's a real problem. It's a congressional mandate. Do anyone remember the rule? It's got some guy's name.
Chuck Grassley?
Okay.
Sorry.
Well, maybe that can change. Politics is...
We can hope.
Any other comments? Not, let's thank Martin.
One of these is mine. This one's mine.
Yes. I didn't have one. Oh, you're good. Thank you. Really interesting. Very important. The first Oops.
Okay, so hi everybody. I'm Samantha Scibelli. I am a postdoc at NRAO Charlottesville, Jansky Fellow there. I started relatively recently, in my opinion, at the end of August, so it's still relatively new. Before that, I was at Arizona, at the University of Arizona in Tucson, and mostly what I focus on is a lot of observational work, looking at molecular lines in the earliest stages of star formation. So I'm going to give you guys an overview of kind of why that's important, and then also talk specifically about one particular paper I'm in the process of submitting, studying these complex organic molecules in cold clouds in the Perseus molecular cloud. So the types of chemistry that I'm talking about, specifically that I'm interested in, are complex organic molecules. You might have heard that term maybe, or COMS. And the reason why a lot of astronomers or astrochemists are interested in these particular molecules is that they are, not signs of life, but they are the precursor species to the molecules important for life, for amino acids, DNA, RNA, and the fact that we're detecting them in the ISM is really interesting because from just a chemistry standpoint, how are these things forming? How are they being transported to different stages in the ISM, et cetera? And so if we want to, answer these questions, especially if we're trying to understand how these things are important for the emergence of life on Earth, I'd argue that one of the best places to search for these types of molecules is in low mass star formation, the type of sequence that forms stars like our sun, where you have a molecular cloud of dense gas that forms filament type structures, and then you have cores forming that are generically called starless cores. Once those cores kind of collapse down, are dynamically evolving, gravitationally or pressure bound, then they're called prestellar cores, and then eventually you'll get a protostar, protoplanetary disk, and then mature solar system like our own. And in all of these stages, complex organic molecules have been detected. And so this is really interesting to try to understand, well, okay, if we see these molecules in each stage, is there a degree of maybe chemical inheritance that gets passed on from preceding evolutionary stages? And there is evidence to suggest this. Actually, if you look at the abundances of these complex organic species when they're compared to methanol, which is the plot over there, on the y-axis is abundances of towards the protostar 16293b, and on the x-axis is our abundances for the comet 67p. And you can see that there's a tight correlation here, and this actually does suggest that these COMs, at least some of them, could be inherited from the cold prestellar core phase. And so this hopefully then motivates to you all why studying complex chemistry in this early cold phase is really interesting and something that I'm interested in studying. However, before my thesis work and before my work, there'd really only been a handful of cores that had had higher complexity species detected towards them, such as the famous TMC1 cloud. And so the question really remains, well, if we want to try to understand how these molecules are forming and their prevalence in this stage, we need to look at more typical cores and to understand, are they common even in this early stage of star formation in typical starless cores? So during my thesis, I answered this question a little bit towards specifically the torus molecular cloud. So here you'll see the first survey that I did was with the Arizona Radio Observatory 12 meter. That's me down there, my first night observing. And you can see that I studied 31 cores along this filament. Finding a prevalence of methanol was detected in all of the cores, and acetaldehyde, kind of this next level of complexity, was detected in 70%. And then I went even deeper to look for even higher complexity species in this L1521E core that's kind of adjacent to the filament, finding even higher complexity species. But the question remains, and something I'm still interested in, is, okay, this is great. At least we know that COMs are prevalent, say, in the cold starless phase in the torus molecular cloud. But what about other environments besides torus? Do we also see a similar level of complexity? And so this then leads to this current survey paper that I'm wrapping up now, where I looked at 35 cores in the Perseus molecular cloud shown here. Again, we started out with the Arizona Radio 12 meter dish. Due to some improvements in the back end of the telescope, we're able to search for not only methanol and acetaldehyde simultaneously, but also this nitrogen-bearing species vinyl cyanide. And from this initial survey with the 12 meter, we found, again, methanol in all of the cores targeted, acetaldehyde in 50%, and in vinyl cyanide, 0% from this initial detection. And so if we want to first compare this to, say, to our torus sample, we really have to understand that these clouds are at different distances. So if you were to, say, scale this, the torus sample, given the sensitivity limit of our survey, you would expect that the torus at the Perseus distance would give you roughly a 26% detection rate. So the fact that we're detecting this acetaldehyde molecule in particular at 50% is telling us that COMs are prevalent, still just as prevalent in Perseus, if not more so. So what we did next was to actually try to search for even more higher level complexity. We used a different telescope. This is the Yebes 40-meter dish in Spain. And we looked specifically at a subsample of these cores, 15, that showed bright acetaldehyde measurements, and looked in a large bandwidth to search for additional comms. And so I'll just go through kind of what we see. We see 5-atom molecules like ketene and formic acid, which I am showing here. Methylcyanide, nitrogen-bearing species here. We do actually see vinyl cyanide when we go to these frequencies at their more favorable transitions. So in a few cores, we do see this molecule. And then we see even higher complexity 8-atom molecules methylformate in several of the cores, and the 9-atom molecule dimethyl ether in several of the cores as well. So now that we have our detection statistics, one of the main things that we want to do is get abundances, right, and then try to compare these to other cores. So that's what this plot is showing. On the y-axis, you have abundances of different complex organic species when compared to methanol, and then on the y-axis is for different cores. So all the orange is in the torus molecular cloud, and then encircled in pink is the Perseus sample that I'm presenting here. And you can see that we've at least doubled the statistics for COM detections in cold cores. And there's actually interesting trends already that you can pick out. So the oxygen-bearing species are the circle points, and they are similar within a factor of a few across different environments. However, when we're looking at the nitrogen-bearing species, which are the square points, you can see that they're up to 2 orders of magnitude lower in Perseus. So this is something interesting. Perhaps there's different chemical conditions in the cores, or they're evolving at different rates. There's lots of, can dig into this chemistry a little bit more to try to unwrap what's actually happening in nitrogen-bearing versus oxygen-bearing species. So, in order to do this, one of the big questions that I want to address more when as a postdoc, as a Jansky Fellow at NRAO and working with chemists at UVA, is to really understand the formation mechanisms of these molecules, because, gas phase chemistry in, say, warmer regions like protostars, the gas chemistry is relatively well known. You have actually, an internal heating source that can get stuff off the grains and get forming. But of course, in a cold, dense prestellar core that I was talking about, you don't have this mechanism. So you need something else to get these molecules off the grains. And so a non-thermal desorption mechanism is one way. And I'm working with Rob Garrett at UVA to try to model the complex chemistry in a subsample of cores using realistic physical conditions in order to try to reproduce the abundances that we see. So this is still ongoing work, so stay tuned for more in the future on that. And then my summary, basically, there is a prevalence of complex organics in the earliest stages of star formation. So that's the main takeaway for you all. And if you're interested in learning about additional results, projects that I did not have time to mention, I'll be giving the RMS seminar tomorrow as well. And so I think I'm at 10 minutes, so I'll leave it open for questions.
This is wonderful. Questions, comments? Yes, please.
So this is a sort of an ignorant question, so forgive me.
Oh, no
I've
questions
got
are no.
millimeter or 4 millimeter spectral, so I've done a lot for somebody who doesn't work in that area. There's very large numbers of low surface noise lines. And I'm just wondering, how secure are your identifications of specific molecules?
Yeah, so for most of the molecules, we have additional transitions. So they need at least, to be a secure detection, they would need at least 2 transitions detected at the 3 sigma level. But as you saw, there were some question marks because, for example, some of these also asymmetric rotor type molecules, you have like splitting an AA state. So you can see for dimethyl ether, you have not only an EE, AA, AE plus EA state. So you can have that you have that nice 3-peak feature that For this one has a question mark towards it because it appears that we only see the brightest center EE state, but we don't see the other ones, so that's a questionable detection. For some of these other ones, right, for vinyl cyanide, we see a bright peak at only one transition, but not another one, so these ones are not as secure, which is why there's a less than 34 instead of a direct detection. But for the most part, if we see multiple transitions based on like laboratory spectroscopy measurements of these transitions, then we're confident in a detection.
In principle, to expect multiple transitions, you need to know something about the atomic physics of the emitter.
Right, and again, we also, because a lot of these, you just have to assume LTE, right? So you just assume a singular excitation temperature, which is likely not true. And so there could be lots of different cores that have other transitions versus another one, so yeah.
Yeah, I was wondering, the analysis of meteorites shows very large numbers of amino acids. And I wondered if you're sensitive to those as well.
So that's interesting. So there haven't been like simple sugars. I think people have tried to look, for example, glycoaldehyde, which is kind of the simplest sugar. It has been detected in protostars, but not in dense cores yet. We're kind of trying to push the limits for some of these like higher complexity things that are more tightly related to amino acids and like DNA and RNA. I think I have maybe that it shows here, right? So like here's, for example, an RNA world scenario, and these are the types of molecules that are important for it. And so for glycoaldehyde is one of those, and it's been detected in a protostar, but we're looking in the cold dense cloud, so we'll see.
If you detect them, they would be sweet, right, with sugar.
Yes, exactly.
I have a novice question. So how well constrained are the abundances of these complex molecules in the pre-core stages, like even in the envelopes of AGB stars or in the not yet dense parts of the clouds?
Yeah, that's a good question. So there have been detections of methanol specifically in like diffuse clouds as well. And people are looking in AGB stars or in like the envelopes of like protoplanetary disks too, and they do see complex organics. So there have been abundance and constraints on those in other stages. So yes, they have been detected in those. I think it's still a question of a bottom-up or top-down kind of scenario of like how these molecules are being inherited, forming first, or if like if the environment is enriched with them, and then I think there's a bit of both. But if that's kind of the question that you're going to, but yeah.
Okay, well, let's thank Samantha.
Okay, hello everyone. I assume everyone can hear me. Let me know if that's not the case. My name is Jenny Calahan. I'm a postdoc here at the CFA, also pretty new. And today I'm going to tell you about a project that I've been working on just for the past month or so, all to answer the question of what happens in the planet-forming region under different radiative environments. So to motivate this, you just saw this figure, which is actually quite convenient. We didn't plan that. But I'm thinking about protoplanetary disks in particular, and these are the environments in which planets are going to be forming. And out of the planets that we have detected so far, the vast majority of them actually reside within 1 AU of their host star, so very close to their host star. And when we think about our solar system as well, we're very interested in terrestrial planet-forming situations, and that's happening within the first few inner AU or so. In the protoplanetary disk, this region corresponds to where the disk is emitting in the infrared because it's fairly hot from 500 Kelvin and above. And when you talk about infrared emission, we're going to talk about J2ST. And at this point, there are 100-ish disks that have promised time on the JWST telescope, and these are a few examples of them. This is pretty typical, where we see a lot of bumps and wiggles in these spectra, and every single one of these lines corresponds to a molecular or atomic transition. So these are information-dense observations. It's really, really exciting, all coming from the main planet-forming zone. Now, how do we start to interpret these observations? We're starting with slab modeling, so we can get column densities and temperatures out of these observations. But to understand the trends that are starting to come to light, we really need to focus on thermochemical modeling, and that's where I come in. So thermochemical models will take in an assumed physical structure, an assumed initial chemical abundance, a lot of other assumptions go into the very beginning, and it will give you a final temperature and a chemical distribution of whatever molecule you're interested in, and then you can make mock observations directly to compare to observations from JWST, ALMA, whatever telescope you're interested in. And the nice thing about these models is that there's no machine learning, there's no AI inside of them, so they're a little slow, they're a little clunky, but you can peer into the mechanics of this model, and you can deeply understand the physics and the chemistry behind why you see the trends that you are able to reproduce with these models. And so there are a lot of parameters that go into the thermochemical model that I'm running that also impact the planet formation potential of the protoplanetary disk. And each of these factors talk to each other. So it's kind of a complex parameter space that has not been well explored, especially when focusing on the inner few AU of the disk. Of course, there's also temperature. Temperature is not something that I give as an input for the model, but all of these impact temperature, and temperature will go back to impact things like the chemical abundances. And there's a lot of other subcategories that we can explore. So disks have substructure, they're complex objects. There's also a time dynamic that I'm not including in these models. But for this talk in particular, I want to focus on what happens to the background radiation field and how that impacts what we see with JWST spectra. And I'll modulate that a little bit with disk mass as well. So the motivation behind exploring the UV background is that the vast majority of disks that we've been spending a lot of time on understanding in the past 10 years or so are kind of unique. They are isolated, they are not surrounded by a lot of neighbors, and they're fairly bright and massive. So we have beautiful data from ALMA and other telescopes of these disks, but they are not necessarily representative of typical planet formation. Most planets are going to form in something like the Orion Nebula, which I'm showing here, that have a lot of neighbors, including O and B stars, that are going to strongly impact the background radiation environment. So when we're talking about an isolated system, we call Witt, that's 1 G0. We can go up to millions of G0 if you're within 0.05 parsecs of an O star. So this is quite a stark difference. But I would argue this is actually typical of planet and star formation. So my experimental setup, I have two disk structures. I assume kind of a typical mass disk and then a low mass disk. And I see how these are impacted by 7 different steps in UV background from the isolated case to very, very close to an O star case. And just jumping straight into the results, we have mock JWST spectra here, and I'm showing 2 examples. One thing that is clear is that every single molecule has its own story. It's impacted differently by the UV field. But one trend I am seeing is that you have to go up to 10 to the 4 G0 to have much of a strong impact on your JWST spectra. If we focus on water, this is a water spectra. OH does the same thing. It is strongly influenced by the UV background. So beyond 10 to the 4 AU, your overall flux is going to explode. It's going to increase by orders of magnitude than what you would typically expect for an isolated case. And not only is the flux increasing quite a bit, but also the shape of your spectra is changing. So these are roughly colder water lines. These are hot water lines. The ratios between these 2 components is changing significantly. So that's kind of helpful. There are other things that will increase the water abundance, and hopefully the ratios can help us break some of these degeneracies in the future. If we look at a different molecule, totally different case, C2H2 seems unaffected by the UV background. It's not doing anything. Which is quite fascinating. And so we can look into the thermochemical code and understand why we see what we see in the mock spectra. So these are temperature plots, kind of in funky plotting units, so height over radius versus radius and log scale. And what I want you to see is that as we step in UV background, the temperature is changing quite significantly, especially beyond 1 AU. It is getting hotter. And this transition between the 100-ish Kelvin gas to 1,000 Kelvin gas is lower and lower in the disk itself. Overplotted on the temperature, I have where the water is emitting from. So this is from the brightest few lines of the water spectra. And so you can see in our isolated case, and we already know this, that the water that we're probing is coming from really, really high up in the disk because there's a lot of water. It becomes optically thick at fairly low densities. So we're probing kind of the tip of the iceberg of the water abundance. But as you increase your UV background, that spatial extent that the water is emitting from is increasing. And in this really extreme case, the water is actually coming from far out in the disk, beyond 10 AU, from these really, really hot temperatures. So that explains what we're seeing in the water spectra. A bit more of a general understanding of what's happening in the disk. I find that there are two primary important zones that are impacting what we see with the JWST spectra. So there is a region that is fairly well shielded from whatever is happening in the UV background, and then the vast majority of the spatial extent of the disk will be strongly impacted by the background radiation field. The boundary between these two regions strongly depends on what you assume for your disk structure, and I think it strongly depends on what you assume for the dust in particular. So where this boundary kind of intersects with the midplane is going to be a critical component when you're thinking about planet formation. And in my typical mass disk, this was around 5 AU. In my low mass disk, this was around 1 AU. So now we can start to understand what's happening with different molecules. For this example, we have water again. So we're now looking at the abundance of water, and you can see that we're only probing the tippy top of the water column. And as you increase your UV background, you're destroying water where it used to be up here, and you're creating more water farther out in the disk. And so you're still seeing water, it's just coming from a vastly different location within the disk. And then we go back to C2H2, start to understand why we don't see any changes in C2H2. Well, if we look at the abundance, we see two distinct reservoirs. We have really, really hot C2H2 coming from within 0.1 AU. Then we have this warm reservoir of C2H2. And with our JWST analysis, we only see the hot C2H2. And the hot C2H2 seems to be totally protected from the UV background, and it's not changing at all. But this warm reservoir is changing quite significantly, especially in the midplane where planets are forming. So this is extremely important to keep in mind. And it's good to know that JWST is not exactly probing this region, but there can be a lot of extreme changes in the background. So my overall conclusion is that these extreme UV environments will impact the chemistry of planet formation. I say extreme, but I think this is actually quite typical. And so all the knowledge we're learning from about protoplanetary disks from isolated disks cannot necessarily transfer over to these really extreme environmental conditions. More specifically, I think there's going to be hot water in the atmosphere, oxygen-rich molecules in the atmosphere of highly irradiated disks, and then there are going to be more organics in the midplane. So we use the C/O ratio to make connections between exoplanets and protoplanetary disks. This is going to impact that kind of characteristic that we use to connect these two. Another big takeaway is that there is complexity in the three-dimensional disk that is not intuitive when you look at JWST spectra. If you just included slab modeling and looking at the spectra, you would have no idea that things like C2H2, HCN are going to be impacted by these different environmental conditions. And there's lots to take into account. This is kind of a first model run. I think there are a lot of directions to go in after this for follow-up. But at this point, I'm happy to take any questions. Yeah.
You consider the UV from stars, but in principle, near an AGN or equator, there might be the flux could be far greater. Did you consider that?
I have not considered that, but I think that would be really fun to consider. That's an extreme environmental condition, and I think we can start to probe that with JWST. I am motivated by observations. With ALMA, it's difficult to probe disks all the way out in Orion, but with JWST, it's going to be really, really easy. So that was another motivator behind this. I think it'd be really interesting to look towards the center of our galaxy and see what star and planet formation is like there. That's something we haven't explored. So we also want to see what impacts does the metallicity have on your chemical environment. So there are a lot of fun directions to go. And so we've not done that, but I think that'd be a fun experiment. Yeah.
Comments, questions?
No one did so.
Yes, Marcus?
Sorry. Your spectrum was just the UV spectrum, but O-stars are big X-ray sources. So
Sure.
can you imagine what will happen if you turn on X-rays?
Absolutely, I can. Yeah, so that's that's another thing that we can put into our chemical model. One interesting thing is, like, my understanding, and this is a little bit outside of my area of expertise, is that especially X-ray like flux will change over time, and so that variable condition I think could really have a strong impact on the chemistry and maybe leave a signature that stays longer than the actual X-ray fluxes that might come out of an O-star or something similar to that. So it will strongly impact the chemistry, especially in the atmosphere. Not sure if it'll make its way to the midplane, but that's something we can run and experiment with. Yeah, thanks for that.
One thing that the X-rays can do is release free electrons, and that changes the chemistry for some molecules.
Absolutely, absolutely, yeah. Yeah, anything to ionize our molecules will strongly impact the chemistry. It's kind of, yeah, a rain down effect as well. Yeah.
Any other comments? If not, let's thank Jen again.
No, of course, yeah, thanks for the question. It's a long, hour. Yes.